All right. Hi, folks. My name is Taylan Topcu. It's been a pleasure hanging out with you for the past couple of days. My research group is called Socio-Technical Systems Engineering Lab. So what we do is we look across the technical product and the social organization's architecture to leverage this interdependency between the social and technical for more effective systems design and management. And this talk is titled In Pursuit of Better, Faster, and Cheaper Complex Systems Realization, and I will try to tell you a little bit of what we mean by that. So as a systems engineer, one of the things that we study inherently is things that are complex, and we define this complexity as an emergent property of systems arising from these parts interacting from non-simple ways. However, as the systems engineering community, we keep blaming complexity for our acute shortcomings that are usually manifested in scope and schedule overruns across the system lifecycle, so not only design. And this is manifested in weapon systems development, but it's not a Department of Defense issue, really. It also happens in civil infrastructure projects, automotive industry, even NASA, who has been developing complex systems, one-of-a-kind complex systems, really, since forever, was 8 years delayed to put the James Webb Space Telescope into orbit. And then there's the notorious F-35 Joint Strike Fighter program that has been a huge sink of money. So as a community, we have been increasingly looking into a solution to this problem, which I think would be a very fertile research area for some of our engineering design folks. And this is called digital engineering. So there has been a very strong push from the United States Department of Defense for digital engineering, but it's really not a DoD thing. Industry has been an early adopter of this. And the idea is that we are trying to move away from our traditional document-based approach to designing really large complex systems into one that's driven more predominantly by authoritative sources of truth, which is essentially a collection of heterogeneous analytical models and engineering tools representing the same exact complex engineer system. And we want to use this ASOT, basically, for the entire life cycle from ideation to disposal. And essentially, this is calling for a huge paradigm shift in the systems engineering community. So I'll try to caricaturize this. I like this kind of stuff. The way current systems engineering works is, let's say I have different kinds of domain experts. I got a mechanical engineer and a software engineer and an electrical engineer. They're all working on the same problem. They all have their own unique analytical models. One of them has a CAD model, the other one is something else, whatever. And what they do essentially is they do their work and then they write documents and they keep exchanging this thing among each other. But this is just a miniature version of a single team. Think of this at a very large scale and also across teams that are working for different organizations who might be designing different elements of a system. So what digital engineering is trying to do is, hey folks, instead of you doing your work in your local data silo and then pushing it through a document, passing it along, carrying a lot of handoff workload, why don't we use this authoritative source of truth? And we pass our information into this. It's essentially a digital whole, a digital ecosystem that retains everything. So we push the information here, we pull the information here, we can communicate faster. Well, we can do a lot of things we do with systems engineering way faster using this paradigm. So, however, there's a huge research gap here, and the idea here is that even though there are really high expectations for digital engineering transformation, number one, its value is poorly understood. Number two, our organizations are pretty large legacy organizations that are composed of folks who are not really used to this digital way of doing things. There's a lot of resistance. And number three is we are not really thinking as much about post-digital engineering transformation. What can we do better? How can we reimagine systems engineering? And perhaps AI could achieve us to do that. So I will talk a little bit about digital engineering more, and I know this is an AI thing, I shouldn't be talking about this, but I'm talking about this to you because I think it's an opportunity for you folks. And I will glance over two of our funded research projects in our group. So this one was funded by the Department of the Navy. The idea is, usually we don't really design things off the scratch. We have these really large systems of systems. We want to operate them as much as we can because we invested so much in it. Let's say I have an aircraft carrier, I want to use it as much as I can. And the problem is I have to keep it updated because new sensors, weapons, et cetera, new technologies become available, things break down, and I need to fix it. Well, these tasks are routinely overscheduled. So one of our aircraft carriers right now is going to be docked for 5 years total now. So we were trying to understand by studying these design teams how exactly the process looks like right now, and how do these design teams need to work with the rest of the enterprise ecosystem to use these different kinds of analytical models to do their work. So we used model-based systems engineering diagrams, essentially UML sequence diagrams, to extract the process. And then we started capturing data from the organization regarding task distributions, and we started simulating, number one, how things look like today and how it's distributed, but also we created a hypothetically digitally transformed version of the same organization, and we tried to investigate how could digital engineering help. So the first box is how the process looks like today. This is the preliminary design phase of a post-production design process. Median day for a project is 196 days. And the second box is how it can be post-digital engineering transformation. And this is without AI. And we actually found that, well, if digital engineering actually works, you can reduce your cycles by 50%. And also, standard deviation also reduces drastically, so you can become better at predicting how long your design cycles are going to get, which is awesome, but it doesn't really tell us much about what are the gains. So what we wanted to do was we coded what kind of things these large engineering teams are doing, and then we observed that, man, these gains are actually totally unevenly distributed. So for certain things such as system-level modeling analysis, there are huge opportunities for gains through digital engineering transformation, but in certain areas, such as review meetings for preliminary design phase, not as much as expected. This led us to ask questions about, man, this is just digital engineering without any AI. But digital engineering can really empower AI. So what happens if I start throwing AI into it? Which parts of the organization can I start injecting it? And this is actually another project funded by the National Nuclear Security Administration through the Systems Engineering Research Center. So the idea here was, well, we've been spending a lot of money for digital engineering adoption, but what do we do afterwards? How can we realize complex systems faster and cheaper that are better and safer? So we wanted to see if these off-the-shelf AI tools, such as large language models, can help generate systems engineering artifacts. And as some of our speakers highlighted over the past couple of days, we are, in the world of systems engineering, dealing with ill-defined problems, not very well-defined ones. There's also a very huge shortage of data. So we started experimenting. We took a notional systems engineering problem, and then we paired a human with an AI agent, and we started generating systems engineering artifacts. And we were able to actually generate artifacts that look exactly like human-generated ones. And when we asked natural language processing algorithms to differentiate them, they were unable to differentiate which one was created by the human and which one was created by the agent. However, when you dig into these artifacts, they are extremely poor quality. And this is really difficult to detect by the machine. So this really, this led to a publication in systems engineering. But this really led us to believe, well, maybe for problem formulation, it's not really there now, but maybe it can be more effective for different kinds of things, because since, again, remember, we are working with these large organizations, people have different roles. So one of the problems is the key decision makers, such as program level managers who hold the money and make the big decisions, actually don't really understand domain expertise most of the times. Maybe they understand one domain. So what we wanted to find out was, can AI help us facilitate communication between the senior leaders and the people who are actually doing the work? And we wanted to see, with my colleague Paul Locke from Virginia Tech, whether if we can use AI to generate model-based systems engineering artifacts into text, and from text back to systems engineering artifacts, so that we can facilitate this communication. And we actually found out that if we use MBSE artifacts in conjunction with language text, we can actually do better, which is great. So that gave us some confidence. And then if we can start doing this kind of stuff, perhaps we can start creating these agents. Oh no, come back. We can start creating these agents that can help assist humans, and this is a very early stage prototype, but interact with these model-based systems engineering artifacts and maybe help explain some information or pull information or edit them without these people having to learn that specific modeling language. And I've been talking too much, but we were thinking that, well, if I can do this at an early stage, what I can actually do is I can start formulating a notional agentic AI framework where I can treat these LLMs as a human interface and as an orchestrator, and wrap things around the orchestration framework that has certain modules that are domain expert modules. Some of these can be ontologies, some of them can be something about how do I requirements, so it's more like a knowledge-based, old-school rule-based model. And then I can even infuse the existing processes of the organizations that we are trying to work with to make these models way stronger. So that's what we are working towards right now. And one last idea about rapid system realization, and I will shut up. I know it's been too long. But one of the other problems is things, as I was talking about, are taking too long for us. And I was thinking, with my colleague Andrea Frito from Virginia Tech, is that man, instead of approaching these problems from a top-down approach, why don't we approach them from the bottom up, prioritizing what commercial off-the-shelf parts are already available to us? Can we then perhaps leverage this authoritative source of truth that provides me with a rich library of whatever is available, and I can maybe create an integrated design framework leveraging control code design, where we can intelligently generate alternatives and very rich descriptions of these alternatives as well, and push these into digital environments where we can automatically test and evaluate. And then perhaps if I can do this rigorously enough, maybe we can realize systems faster. So to wrap up, there are many opportunities in the systems engineering area, and I think digital engineering can provide an opportunity for EDSC community to merge in this area. If you folks are interested, I think a lot of your analytical skills can translate very well. But it's interdisciplinary problems that necessitate a lot of tacit knowledge. We think there are a lot of opportunities in context-aware and lifecycle-aware approaches of AI. But there are a lot of challenges. Primary one is the open-ended problems. Systems engineering also lacks a theoretical foundation. That doesn't really help. And there's a lot of lack of data. I mean, this keeps getting repeated, but the kind of data we need is data across the lifecycle, because at the end of the day, I don't really know which data is good or bad until I have some access into design rework and all the issues that came with it. On that bright note, I'll shut up now. Thank you for your patience. Thank you. Do we have time for questions? Okay. Questions? Ali.
Can you maybe speak to, what was the reason for slow adoption of digital transformation? I think as engineering community, we use generative models,
right.
models of every time, and digital transformation was, let's use that for, system design purposes.
Actually, that was primarily the root cause of the problem. People thought, wow, I have these new tools and technologies, let's invest millions of dollars and make it available to my organization. But the thing is, it's composed of folks who like their own models. They want to work with their models. They don't want to be told how they want to do their thing. So we recently submitted a paper, and there's a preprint available called Socio-Technical Barriers to Digital Engineering Transformation. It's on ArchiveX. I'll be very happy to share. So it's a very high-dimensional problem. Humans are at the core of it. Thank you.